Hello everyone, thank you for coming to the NSF-PIRE workshop. My name is Zhongkan, a PhD student at KSU, and I'm going to present the work has been done in 2019, which is the SiOC fiber mat via electrospinning from cyclic precursors. For today's presentation, I will cover the following contents. Let me briefly go through the motivation here. We know that ceramic matrix composites, or CMCs, are desirable material for turbine engine applications. It can greatly increase the fuel burning efficiency. Currently, PDC fibers are the major reinforcement for CMCs. Okay, let's look at our product before going deeper. We were able to obtain the fiber mat of approximately 15 centimeter by 15 centimeter, and then we can then cross-link them entirely in a low temperature oven at 160 in air. And then we were able to pyrolyze them at 800 degrees Celsius in argon. And then as you can see, the obtained fiber mats are free of warping. And then the shrinkage was about 20 to 30%. Last year we presented hand spinning of siloxane. However, this year we moved over to siloxanes. There are several reasons for it. Firstly, we noticed that during the spinning process, ammonia gas was formed in terms of siloxane. However, siloxane doesn't have this problem. Secondly, siloxanes are much cheaper and then more readily available in the market. And then for last, we were able to obtain these very similarly structured siloxanes that will ultimately give us the SiOC ceramics. Therefore, we chose this year the siloxanes. And then PVP is used as a spinning reagent. And then isopropanol is the solvent for PVP. And then 1% DCP was used as a cross-linker for 4 TTCS, 3 TTCS, and then DTDS. But the platinum TTCS is a complex of platinum and then 4 TTCS. So platinum will work as the cross-linker itself. This electrospinning setup was designed and assembled in our lab, where it has 4 different major parts. The extrusion part is precisely controlled by the step motor, and the step motor is controlled by the Arduino control system, and then extrusion system and then collecting system are connected by this high voltage power supply, where the positive side is applied on the needle tip and then the ground is applied on the fiber collectors. This schematic shows the very detailed manufacturing process of the electrospun fiber mat. Well, firstly, we have to prepare the solutions, and then PVP is used as our spinning agent, where you can see we can have maximum of 400% loading for PVP, and then after the spinning, the fiber mat can be generated. This is a video clip of electrospinning process. You will see at the needle tip, there are solutions coming out of it, and at a certain point, it converts to numbers of fibers, and then it gets attracted to the right side. This video clip is the slow motion of the previous video clip. We can see that the fibers are stretched suddenly and becomes very long. Then it gets attracted. Okay, let's move on to the characterization part. Here are some SEM images for our electrospun fiber mats. As you can see, the fiber diameters are very uniform, and then the diameter distribution is well controlled. So the average diameter is ranging from approximately 2.5 down to 0.6 micrometers. So this slide shows some TEM images and then EDX information. And then TEM shows pretty much the same information as the ICM. Well, you can see the diameters are at maximum 2 microns down to 600 nanometers. Okay, and then the one thing to notice is that platinum signals are detected in platinum TTCS even after pyrolysis. Raman spectroscopy, we were not able to obtain a good signal from platinum TTCS sample. You will see a very strong fluorescence, and I believe this is coming from platinum. But after we remove the background, you'll see the G band has a much stronger signal than D band. This can be explained from the XPS. FTIR is performed to determine the cross-linking behavior of the samples. We did the pristine PVP first to confirm that PVP doesn't get involved in this cross-linking process. And then you may see that for all samples, the characteristic peaks have decreased but not completely disappeared, which means that the cross-linking happened but not completely happened in the samples. And then XPS is performed firstly to determine the overall composition of the final product. As you may see, the platinum TTCS sample has the highest silicon concentration. And then this may later affect the flame testing. So one thing to notice is that, as we mentioned in Raman spectroscopy, the platinum TTCS sample has a very strong G band than D band. And this can be confirmed here that from the high resolution scans, platinum TTCS samples always shows the lowest carbon to silicon bonding, which indicates the phase segregation of this product. NMR was performed also to determine the cross-linking behavior and then the overall final composition. From the most left graph, you can see that the 4 TTCS, 3 TTCS, and DTDS, after the cross-linking, they all form a rigid structure. But the platinum TTCS did not show a very strong rigid structure after the cross-linking. And then also in the pyrolyzed signals, platinum TTCS shows mostly the, I say, all four structures, which means very less silicon to carbon bonding in the platinum TTCS. This result corresponds to the previous XPS result. We have exposed our fiber mass to the acetylene flame torch for 20 seconds, and platinum TTCS sample showed the best overall thermal performance, where it didn't shrink or oxidize on the surface. So 4 TTCS and 3 TTCS showed a slight burn at the surface. However, DTDS showed a complete shrinkage and then burn after the frame test. Here's the video clip of platinum TTCS sample that is exposed to the acetylene flame torch in open air. And as you can see, the fiber mass were holding pretty nicely, and then without any warping or any shape changes. We were able to find some applications for our electrospun fiber mass. Shakir is one of the PhD students of our own at KSU. He made some lithium-ion batteries using our electrospun fiber mat as an anode material, and he did some electrochemical performance test. And then our undergraduate students were trying to manufacture the CMCs using our mat as the reinforcement. And then we also shipped some fiber mats to Lehigh University, where they were trying to use high resolution microscopy and then machine learning to predict the microstructures. In summary, for the first time, we were able to achieve large area electrospun fiber mat from cyclic siloxanes using our own electrospinning setup from all 4 different precursors. Compared to the other literature, we were able to achieve up to 400% precursor loading on PVP. So the fiber diameter was measured to be 0.5 to 5 microns, and then the further characterization showed that the fiber mass cross-linked by platinum had the highest silicon concentration as well as the best thermal stability. So financial support from NSF is gratefully acknowledged. Thank you. Any questions?